Hello everyone, I'm Leah and this is my presentation I made based on my term reports on Kamiak Butte for the class Natural Resource Ecology. My first report was on the geological events that made modern-day Kamiak Butte. These events were sectioned into four main ones: Pangea, metamorphism events, the Ice Age, and the formation of the Loess Hills. Pangea plays a huge part in setting the foundation for Kamiak Butte. Around 240 million years ago, during Pangea, a third of North America was underwater, including all of the Pacific Northwest. Once North America broke apart from Europe and became independent around 80 million years ago, it started thrusting itself over the Juan de Fuca plate. This process is what rose the Pacific Northwest out of the ocean. This event is significant because it's responsible for the Palous's sandstone base. However, we know that modern-day Kamiak Butte isn't made of sandstone, but quartzite. So intense compression and high temperatures had to occur for metamorphism to take place. There are three key metamorphism events that eventually turned the sandstone base into quartzite. The first one was an accretionary wedge. As the Juan de Fuca plate started subducting underneath North America, some of the plate got scraped off and pressed into the land, which eventually formed the Olympic mountain range found in western Washington. This mountain building process compressed the land around it, which contributed the compressional factor for the quartzite. The second event was the formation of volcanoes. The subducting Juan de Fuca plate was also responsible for the Cascade Mountain range by forcing molten rock up through the crust, but the magma didn't have the power behind it to reach the Palouse. The third event, the Columbia River flood basalts, provided the transportation for the magma to get to the Palouse. The combined force of the Yellowstone hotspot and magma from the Cascade Range forced a huge swell of molten lava to flow over the Palouse, providing the high temperature factor for the quartzite. The now quartzite-based and basalt-covered Palouse next underwent an ice age. Glaciers grew and receded multiple times, carving out the channeled scablands, creating giant ripple marks 50 feet high and 200 to 500 feet apart. It also created huge plunge pools such as Palouse Falls, moved big boulders as big as cars and houses into flat areas. This process that occurred during the Ice Age is what set up the formation of the Loess Hills. All the debris that floodwaters carried when the glaciers receded dug up the fertile soils and deposited it into Wallula Gap. The final event that formed the last piece of Kamiak Butte's foundation was the formation of the Loess Hills. Over the course of tens of thousands of years, the marine polar winds from the west blew through Wallula Gap and picked up the Loess soils and deposited them on top of the quartzite and basalt layers, turning the Palouse into the rolling hilled prairie landscape we see today. My second report was about the climate of Kamiak Butte. There are three main things I found that influences Kamiak Butte's climate: air masses, continentality, and topography. Air masses bring a constant temperature and humidity to an area and are responsible for long-term climate everywhere. There are four main types of air masses: Arctic, polar, tropical, and equatorial. There is one main air mass that influences Washington's climate, the marine polar air mass driven by the Pacific Ocean. However, Washington West and East Side have climates that are very different from each other. That is because the Cascade Mountain Range acts as a blockage for the air mass and causes a rain shadow over eastern Washington. This keeps the west side moist and cool, while forcing the east to form a desert-like environment. The continentality effect is described as the difference between marine and continental climates. Even though eastern Washington is usually more dry and hot, it is still influenced by the marine polar air mass, and it can be seen throughout the seasons. During the summer, the marine polar air mass is weaker, and the results are a hot and dry climate. During the winter, the air mass is stronger, bringing a cold, moist climate. There are two types of topography: physical landforms and vegetation. The physical landforms of Kamiak Butte have already been discussed. Kamiak Butte consists of one large hill reaching 3,650 feet in elevation amid a relatively flat surrounding. The topsoil is wind-blown loess soils that sit on top of a basalt and quartzite layer. The vegetation of Kamiak Butte consists of 170 species of plants that thrive on the addition of extra precipitation received than most other parts of eastern Washington. Pullman receives 20.1 to 25 inches of precipitation annually, while most of eastern Washington only receive from 7 to 9 inches. The next term report is about the biome of Kamiak Butte. My report focuses on where you can find the biome elsewhere and both the abiotic and biotic elements within the biome. This biome found on Kamiak Butte is called the Western Interior Temperate Shrublands and Woodlands biome. It is actually very rare and is not found in many places, but there are a few. North America is actually home to one of the biggest amounts of this biome. Some of these areas are the Nebraska Sandhills, the foothills of the Montana Mountain Range, Central California, the prairies in Texas, and the Flint Hills of Kansas. Outside of the United States, we have it appearing in north-central Mexico, with some occurring near the border between the United States and Canada, but decreases further into northern Canada you go. Some popular places in Eurasia where the biome can be found is the Durian Steppe that is located near Mongolia, the Tibetan Plateau that stretches across Asia, and southern Russia, which holds the South Siberian forest steppe. This biome is home to a lot of diversity among the biotic elements. Up to 300 plant species could be found on just 3 acres. Most of these plants consist of shrubs, perennial grasses, and forbs. Depending on the precipitation received, this biome can support more woodland features as well. The reason grasses and forbs are found so commonly in this biome is the resistance to cold seasons, extreme heat, fires, and grazing. As many as 3 million insects can be found per acre. They are the key elements in keeping the soil healthy by recycling decomposing material, maintaining soil structure, and pollinating plants. They also provide a food source for animals further up the food chain. The abiotic elements that are commonly found throughout the biome worldwide is the presence of a rain shadow, for example, the Durian Steppe, and the Himalayas. This creates dry and hot temperatures in the summer with moist, cold winters. This biome can only exist in places with a large seasonal difference, so further away from the equator. Another trend is the fertile and well-drained soils made from glacier activity. The fourth term report is about the mesoclimate of Kamiak Butte. I've split it into 3 main sections: the north side, the south side, and disturbance factors. The north side and the south side are completely different. The north side has an abundance of vegetation including ponderosa pine, Douglas fir, and western larch. The positioning of Kamiak Butte allows the north side to consist of a lush forest filled with mosses, ferns, and lichens. The ridge shields the side from direct sunlight, creating lower temperatures and providing more shade for the wildlife and vegetation. The shade also allows water to be soaked into the soil before being evaporated, and retains the winter snowpack longer into the spring, providing more available water for plants. The south side of Kamiak Butte has much less diversity, with ponderosa pine being the only tree able to survive the direct sunlight. Only a few forbs and bunch grasses can survive as well, making the south side appearing more desert-like and barren. Water also has a harder time penetrating the soil since most of it is evaporated. The well-drained quartzite substrate also adds to the lack of water. Disturbance factors on Kamiak Butte have already been briefly talked about: fire suppression and lack of water. On the Palouse, fires naturally occur every 12 years. The frequency of the fires cleared decomposing material from plants and trees. Once humans interfered, fires only occurred every 72 years on the Palouse. The buildup of fallen material causes high-intensity fires to devastate the area. Lack of water is also a big disturbance factor. The substrate of quartzite drains water very quickly, only allowing the hardiest of plants to survive. Moscow Mountain, roughly 20 miles away from Kamiak Butte, has much more vegetation because the substrate retains water more. The less hardy trees such as maple, birch, red cedar, and white pine can grow there. Finally, I chose my last term report to be about the effects of human development on Kamiak Butte. I split the term report into three main topics: the city growth impact, wildlife affected by habitat loss, and solutions. Habitat loss and fragmentation due to city growth is the leading driver of loss in biodiversity. Less than 1% of the original Palouse grasslands and prairie remains, and Pullman continues to grow at a rate of 73% faster than other similarly sized cities. More and more of the environment is being taken away to make room for highways, buildings, and especially agriculture, unless major changes are made. Two animals on the Palouse that are currently being threatened are the moose and the antelope. The moose can no longer take the route through campus when migrating, which lowers their chance to reproduce and maintain genetic diversity. Antelope are currently threatened because the Palouse no longer provides the antelope's main food sources of prairie plants. The antelope are also not equipped for jumping over the barbed wire fences and often get tangled up and die. They also fell victim to the lack of food due to overgrazing by livestock, who also transferred many diseases over to the antelope. Some solutions to habitat fragmentation are wildlife corridors that allow animals effectively and safely migrate across major roads and highways. There are close to 2 million collisions between big animals and cars every year in the U.S. In addition, animal detection systems can also be installed, which alert oncoming traffic of nearby big animals before they approach the road. A few of these systems even let out sounds and turn on flashing lights to keep the animals from approaching the road. When these structures are implemented, collisions between cars and large animals are reduced by 97%. Another solution is to simply remove the unnecessary barrier structures such as fences, walls, and dams. The ones that must remain could also be replaced by fences that wildlife can safely maneuver over or under them. Dams can also be modified to have a lower or reduced size. A Germany company called Smart Hydropower have invented turbines that can be implemented within rivers and streams that generate electricity without disrupting water flow.